All right, so in 7.2, we talked about sampling distributions of sample proportions. Now we're going to talk about sampling distributions of sample means. Remember, a sampling distribution, kind of the gist of what we're talking about here is if we take many random samples of all the same size. So like, I don't know, if we take many random samples of size 20, okay? And we take all these random samples, and on each sample, we calculate either a proportion or a mean for that sample. We get a sample proportion or a sample mean. And we look at all these random samples of that same size 20, and each one has their own sample mean and sample proportion, and we look at the distribution of those sample means or those sample proportions. That's what a sampling distribution is. That kind of makes sense, hopefully. I know that these can be kind of tricky to understand, but I've had questions emailed to me about sampling distribution. Some, I don't know if it was this class or the other class, but I've had multiple questions about that. And I wanted to kind of address that today and try to clear up that confusion with that. Okay, you're taking many random samples of the same size. 20, for instance, is just a number I'm throwing out. But it could be 100, whatever. Each one of those samples has a sample mean or a sample proportion. And you collect all those sample means and sample proportions and look at the distribution of those. That's what we're talking about. Today we're looking at sample means. Okay. So, after this lesson, you should be able to find the mean and the standard deviation of the sampling distribution of a sample mean. Get tongue-tied there. Mean and standard deviation of those, which, by the way, formulas on your formula sheet is 2. They're there. You do have to check the 10% condition, though, before calculating the standard deviation of a sample mean, just like we did with proportions. That 10% condition still applies. Okay, that means that the sample size, n, has to be less than or equal to 1/10 of the population size. So if the population size is 200, my sample sizes can only be up to 20. They can be 10% of that. I can't have sample sizes of 40 in a population of 200. That's too big. You're also going to explain how the shape of the sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. And if appropriate, use a normal distribution to calculate probabilities involving sample means. So we're looking at the sampling distribution of X bar, the sample mean. X bar is your sample mean. We talked about that notation in the first section of this chapter. P hat's the sample proportion, what we did in 7.2. X bar is the sample mean, what we're looking at here in 7.3. So when we record quantitative variables, we're interested in other statistics such as the median or the mean or standard deviation. Sample means are among the most common statistics. Okay, remember, a statistic comes from a sample, a parameter comes from a population. Statistics estimate parameters. So consider the mean household earnings for sample sizes of 100. Compare the population distribution on the left with the sampling distribution on the right. What do you notice about the shape, the center, and the spread of each? We'll start with the shape. What do you notice about the shape of these distributions? What about the distribution on here on the left? This one. I know it's going to be a little hard to see with the recording. This distribution right here, how is it shaped? Is it symmetric? Is it skewed? If it's skewed, which way is it skewed?
It's skewed to the right.
How do we tell whether it's left or right? Let's remember how to do that, because that's definitely something we want to hold on to. That's prior knowledge. Does it have to do with the hump or the tail?
Isn't it the tail?
It's the tail. So which way is the tail going?
Right.
It's going to the right, so it's skewed right. Okay, it has to do with the tail, it's skewed right. Okay, what about this one? How is it shaped?
It's symmetrical.
It is symmetric, so it's symmetric, and if you really, like, we're kind of got a really wide window here, but if we kind of zoomed in on this, it even kind of looks a little bit bell-shaped. What distribution has a bell shape?
Yeah.
Which one has bell-shaped and symmetric? Single peaked. It's a big distribution that we've talked a whole lot about. We'll come back to that. That's okay. It is symmetric. That's the main thing. So we're comparing them here. Centered. The population distribution mu, mean right there. It's centered right there about just a little bit below 100. How does that compare to the center over here? Pay attention to the scale, but it looks like the scale on both of these is the same. So that one's centered at 100, whereas this one's, or not 100, but a little bit below 100, and this one right here is centered a little bit below 100. So they have the same center, basically. Even though that one's skewed right and this one is symmetric, they're centered at the same value. What about the spread? Well, obviously that one over there is going to have a wider spread than this one. So the spread is a little bit less. That's all we can really say about that from just the graph. All right, so when we choose many simple random samples from population, the sampling distribution of the sample mean is centered at the population mean, mu. They were centered at the same value. We said that. So the mean of the sampling distribution of X bar is going to be mu. The population mean. All right, but the spread, it has less spread than the population distribution. So here are the facts. The mean of the sampling distribution X bar is mu sub X bar, which is mu, just mu. It's the mean population mean. The mean of the sampling distribution of X bar is just the population mean, same mean. But the standard deviation, it's going to be your population standard deviation divided by the square root of n. Okay, the square root of n. And I'm not really sure if we'll get into how that's derived there, how that comes about. But that's the standard deviation. These formulas are on your formula sheet. That's all, of course, as long as the 10% condition is satisfied. So little n, the sample size, has to be less than or equal to 1/10 times the population size. You have to check the 10% condition first. All right, so these facts about the mean and standard deviation of X bar are true no matter what shape the population distribution has, whether it's skewed or even if it's symmetric. All right. We have described the mean and the standard deviation of the sampling distribution of the sample mean X bar, but not its shape. That's because the shape of the distribution of X bar depends on the shape of the population distribution. In one important case, there is a simple relationship between two distributions. If the population distribution is normal, that's what I was looking for a while ago. Bell-shaped, symmetric, normal. Normal distribution, guys. Bell-shaped, single-peaked, symmetric distribution, normal. If the population distribution is normal, then so is the sampling distribution of X bar, automatically. But hey, we just did one where it was skewed and the sampling distribution was still normal. So sometimes the sampling distribution can still be normal even if the population distribution is not. What this is saying though right here is if the population distribution is normal, then automatically the sampling distribution is also going to be normal for the sample mean. So suppose that a population distribution is normally distributed with a mean mu and a standard deviation sigma. Then the sampling distribution of X bar has a normal distribution with mean mu the standard deviation of sigma divided by the square root of n. Provided, of course, the 10% conditions met. But of course, most population distributions are not normal. So this is where we bring up probably the biggest theorem. We haven't used the word theorem in statistics yet. You probably are familiar with the word theorem. You've been through high school math. You've heard of theorem. When you think of theorem, probably some big ones that come to mind. Probably the biggest one that comes to mind would be Pythagorean theorem, probably, from all of your years of math. But this is a theorem called the central limit theorem. Most population distributions, of course, are not normal. So what is the shape of the sampling distribution of the sample mean when it's not normal? Well, it's a remarkable fact that as the sample size increases, the distribution of samples means changes its shape. If you increase the sample size, eventually it becomes a normal distribution for the sampling distribution, regardless of what the population distribution is. So when the sample is large enough, the distribution of sample means is very close to normal, no matter what shape the population distribution has. As long as the population does have a finite standard deviation. So we draw a simple random sample of size n from the population with mean mu and a finite standard deviation sigma. The central limit theorem says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. Okay? I'm going to pick on Olivia here for a minute. Limit n getting large. You see where that's going? The underneath part of this. Since you had calculus, I had to. Anyways, the limits themselves is a calculus thing. We're not going to get into the derivation of this or the notation even of this, but there is a connection there. All right. So we considered this strange population distribution from Rice University Sampling Distribution Applet. Describe the shape of the distribution as n increases. Well, as n increases, watch how the distribution changes. As n increases here, it gets more and more normal looking. Okay, it started off with like 3 different peaks, crazy looking. Then it's got several peaks, and then they start to converge and we start to get a normal distribution eventually as n increases. This is just a visual to show you as I increase the sample size. That's what's happening here. As the previous example illustrates, even when the population distribution is very non-normal, it sounds weird to say, very non-normal. Okay, I'm almost say very abnormal, whatever. But it's not normal. The sampling distribution of the sample mean often looks approximately normal when the sample sizes, even with sample sizes as small as n equals 25. But in order for us to have a cutoff here for this, how big the sample size has to be, for whatever reason, and the derivation of it, like I said, I'm not going to get into because it involves higher mathematics that we're not necessarily going to talk about here. But the cutoff number that they like to use is 30. When the sample size is 30 or bigger, and it's just 30, it's just it. Okay, you're just going to have to get over that, and that's just a magic number you're going to have to remember, kind of, for that. If the sample size is 30 or more, okay, bigger than 30, or equal to 30, then no matter what the population distribution is, the sampling distribution of the sample mean will be normal. It'll be approximately normal. Questions? 30 is just the magic number you check for there. This replaces checking the NP and n times 1 minus p, making sure that they're bigger than 10. Remember when we did that? That's how we check for normality with proportions, sample proportions. How we check for normality with means, the sample size just needs to be 30 or bigger. That's it. That's all you have to do. You don't have to really calculate anything. You just got to check that the sample size is bigger than 30 and state that if it was an FRQ. Although you won't have an FRQ with Chapter 7. I do need to get your FRQs graded, and I'm working on those. Hopefully I'll have those done by the end of the week. So the central limit theorem allows us to use normal probability calculations to answer questions about sample means from any observations, even when the population distribution is not normal. Okay, so that's how we check for normality with means. Okay, with proportions, let's sum that up real quick. I want to write this down. This might be something you want to write down somewhere. How to check for normality in sampling distributions.
Are we in chapter 7?
Yep.
Yes.
Yes, 7.3.
Alright, cool.
Yes.
Just making sure.
It's okay. It's okay.
Thank you, Hannah. You're the only one.
You're welcome.
I wasn't judging, I just thought it was funny that we're this far into the.
For sample proportions,
May not be what's going on.
you want to verify
Just-
that NP is greater than or equal to 10, and N times 1 minus P is also greater than or equal to 10. That means your number of successes and your number of failures would be greater than or equal to 10, both of them. For sample means, this is not on your formula sheet either, what we're stating here. Sample means X bar. All you have to do is check that N is greater than or equal to 30. That's it. So this is, of course, this is what we did in 7.2. This is what we're doing today with 7.3. You want to notate that off to the side there too, just so you know which section that goes with. It helps. Especially if you didn't get all the problems done with 7.2, you want to go back and try to finish some of those, that might help. You have to check that. Of course, you also have to check the 10% condition regardless in both cases. You have to check that little n is less than or equal to 1/10 of the population size. You have to do that on both of them, means or proportions. That stays the same, the 10% condition. And that's in order to be able to calculate the standard deviation. Okay, I'm gonna move this back. I just thought that might be helpful to have, to tell the difference there. That's how we check for normality. So we've got our graphic here to kind of show that. We take our population. It has a mean mu. We take simple random samples of size little n. All these simple random samples each have their own X bar, and we look at the distribution of those X bars. They're going to have a mean centered at mu, the population mean, and the standard deviation is the sigma, the population standard deviation, divided by the square root of n. That's why it's a smaller standard deviation on the sampling distribution, because you're dividing by the square root of n. You're taking the population standard deviation and dividing by something. Regardless, it's going to make it smaller. Dividing always makes something smaller unless you divide by a number less than 1, of course. What's your population? Or your n is your sample size, so n will never be less than 1. It's always a whole number. At best, it'll be 1. But if your sample size is 1, you're really not doing very much there. but, yes. I'm missing Abby Gann. Who else are we missing? Jocelyn's virtual, so is mine.
I think that's it.
Okay, that's it. Yes. All right, no problem. Bye. Questions? So let's practice a little bit with this. On page 454. Let's do 49 to 61 odds. Put an S on the end of that. I don't have room for it. And then 63, no, not 63, 65 to 68 all. Let's have some time to work. You still got plenty of time. Not really. It's because why? Is that clock right?
We have an hour. We have like an hour and